Okay, this was the last problem we were looking at last lesson. If you remember, we formulated this linear programming problem. Linear programming problems are optimization problems, and this is a really trivial example, but I'm hoping you can sort of picture how this could be applied in sort of industrial processes where you where you are you're making something that requires some time on this machine and some time on that machine and some time on this machine, rather than you're making a cake which needs eggs, flour and sugar. Anyway, I've revised what we did last lesson. The first thing I've revised is, and it's because I want to solve this using a graph, is I've called our two variables x and y, okay, rather than f and c. So I've made that change, and I've rewritten the three constraints that we came up with last lesson using x and y rather than f and c. So no change there, except I have simplified the flour one because I could divide everything by 250, and I have simplified the sugar one because I could divide everything by 100. And what I want to now do is use a graph to find out where Mrs. Cook's optimal solution lies. Remember, her objective is to make as much profit for charity as possible, and she sells the fruit cakes for £3.50 and the chocolate cakes for a £5. There's a couple of constraints that I forgot, and then there's one big assumption which we didn't discuss. Could anyone suggest one or two additional constraints, limits to x and y, that we perhaps should have stated? What do you think, Ethan?
X and y have to be integers.
Got to be integers? And not just any old integer? Yeah, possibly. Yeah, x and y can't be negative. You can't make a negative number of cakes, and I suppose you can make 1.5 cakes, but we're assuming that she's going to make whole numbers of cakes. So really, I should have stated that x and y should be greater than or equal to 0. Could be 0. She could decide just to make only fruit cakes or only chocolate cakes. But that's good news in terms of solving this graphically, isn't it? Because it now means that I'm only worried about axis, a first quadrant axis. And you may remember how we plot lines like this and use it to define regions. That line there, I just asked two questions. What do I get when x is nothing? Y would be 18. And what do I get when y is nothing? X would be 36. And that line would be a solid line, and I would be interested in the area underneath it. And what a good job, to save time, that I produced a colour copy of this and photocopied it in colour for you all. Well, that was my plan anyway. For some reason, the photocopier isn't working, so I had to print it on my shunky black and white printer. So sorry, you haven't got coloured copies. But the red line is the eggs line, and the blue line is the flour line, and the green line, sorry, I didn't have a green pen, so that's why I've written in black, is the sugar line. And I hope you can see that we are interested in the region where x plus 2y is less than 36, so we're underneath the red line. Hi, Evie, come on in. Go ahead yourself, sorry, no trouble, yeah. We're interested in underneath the blue line, and we're interested in underneath the green line. So, and also above the x and the y axis. So this is the region here that we're dealing with, and that's referred to as our feasible region. But rather than shading it, we shade everything outside it. So we leave the feasible region unshaded. So my sort of shading for this problem is going to be like this. I invite you to shade similarly. I should have made the point that this question doesn't actually ask us to do what we're doing now. Formulating the problem is getting to there, end of. Okay? We're now taking it one step further, but if the question said formulate this as a linear programming problem, that's as far as we would have gone. Alright? So we're now taking this one step further. Okay, let's consider the red egg line. Okay, so everywhere within this region gives us possible numbers of fruit and chocolate cake that she can make, given that she's only got 36 eggs. Okay, so for example, she could make 5 of each. She could make 5 fruit cakes, 5 chocolate cakes. She could make 6 fruit cakes and 15 chocolate cakes. Now, can anyone suggest why a solution on the red line is going to be better than a solution in the middle of the region? What does a solution on the red line mean in terms of her egg usage? What do you reckon, Thurston? Second, sorry? So, go on, add something to that, Frank. A whole number? It's not that it's a whole number so much. She's using all her eggs. Yeah. If we have a solution that's on the red line, it means we ain't got any eggs left over. Here, 5 and 5, that means she's used 5 eggs there, and she's used 15 eggs. She's got eggs left over. So there's waste involved. And, you know, okay, she could use her eggs for something else. But in an industrial process, you know, not using our resources is a waste. And of course, the same is true of the green and the blue line. So I hope you can see that if there's going to be an optimal solution to this problem, it's going to lie at one of the corners of the feasible region. And this feasible region has a corner here, a corner here, a corner here, a corner here, and a corner here. And in an ideal world, you would be able to read those values from your graph. I suspect you can't. So, 0, 0. I'm hoping you are happy with me ignoring that possibility, because it is at the corner of the feasible region, but it's not very good. So this solution here is that she makes no fruit cakes and 15, 16, 17, 18 chocolate cakes. We've got this solution here, which is that she makes 12 fruit cakes and 12 chocolate cakes. We've got this solution here, which is 19 and 4. And we've got this solution here, which is 21, 22, 23, 23 and 0. Now remember, the profit she makes is 3.5 times x plus 5 times y. So what I'd like you to do is to work out which of these is going to give the most profit. Use your objective function that we want to maximise this with those 4 possibilities, the 4 corners of the feasible region, and let's work out where we're going to find the most profit. That bottom one is 23 to 0. It just so happens that all of our corners are integer solutions, but if they weren't, we'd have to just come in to the nearest integer solution. That wasn't an issue here. Do we have a winner, Jake?
No.
I haven't done it, so I trust you. Are we in agreement? So, and the profit? Don't you say I don't know after every answer, Jake? You just be confident. You're a... Yeah. So 3.5 lots of 12. What's that? 36 plus that's 42, and
60. Yeah, spot on. Yeah. So you know, less profit. So
our best solution, if Mrs. Cook is a mathematician and decides she's going to do her baking by linear programming, is to make 12 of each.
and the fact that that's the same number of each is a coincidence. Don't think the optimal solution, but it's important that you understand that the optimal solution to any linear programming problem will always be one of the corners of the feasible region. Now, that's not the only way you can find the optimal solution, but this is referred to as the vertex method. It's by far my favourite. So you're finding,
We will hopefully have time to look at the other method, but this is, I think, by far the easiest way of finding, once you've got a feasible region, the optimum solution. There was an assumption that we... Yes, sorry.
Could you also do it by, if you put it on in Desmos, the new equation, which is 3.5x add 5y add some variable, and then just the variable from something high until it first hits the...
Yeah, you do. What you do is you make that equal to, you know, something between 0 and 100 and vary it, and then, that's called the ruler method. And that's the second method, which and it's not just in Desmos. You're expected to be able to do it manually. So we'll come to that as well. Does anyone want to state the assumption? Okay, so go.
They're both as popular as each other?
Well, the assumption is she sells them all. Yeah, that's right. Yeah. Of course, you don't sell them, you're not going to make any profits at all. So that was the other big assumption. The assumption is that in this particular case, they all get sold. So what we've done is a full Monty linear programming problem. We formulated the problem and then we solved it with a graph. You are very, very, very rarely, I think I can say with absolute confidence, you'd never be asked to do the full cycle because it just takes too long.
But I think it's worth doing just to sort of try and put it in context. So let's look at a couple of problems. Let's look at one problem where they give you the constraints to start with. So it's out of context. Page 161. There's loads of stuff in this book which I just don't think you need. So we're going to go all the way to 161. 161 and question 7.
Okay. So here is a linear programming problem. This is page 161, question 7, if you're at home and can't see that, where we have 3 constraints. All of the constraints are greater than constraints.
And we are asked to minimise something. So there's no context in here. We don't know what C is. We don't know what these 3 constraints are about. But we're asked to draw a graph. So remember how we draw these graphs? Just ask the 2 questions. What do you get when x is nothing? What do you get when y is nothing? Have a quick go. Let's do this one manually, just to sort of see. If I might say you know what your x is going to be.
So I reckon you need to go to if you go to 200 on both axes. So perhaps 10 centimetre lines maybe? Does anyone want to borrow a ruler?
Not borrow a ruler.
Yes. So if you do 10 centimetre lines and go to, and then each square is 10. And then of course, you could do this on your calculator as well. Now remember, we are interested in this question about a feasible region that's above all three lines. So we're being asked to minimise. So I hope you can see that the feasible region this time is going to be this region here, because we want to be above the 2x plus y equals 60 line, because we're saying where is it greater than or equal to, 160, above the x plus y equals 120 line, and above the x plus 3y equals 180 line. So we've got, this is our objective, to minimise. So what we were asked to do in the first instance was to use the vertex method to identify the optimal point and therefore the optimal value of C, the minimum value of C. Now, again, it may be that you can't see your 0 is that one there. I'll work out that one in a minute. That one is 4080.
Because we could use simultaneous equations to solve that one. We don't need to look decimals.
That is 9030. 9030.
So this is our objective, but this time we want to minimise it.
Yeah, I think yes, Lauren.
1% on 120, 160, isn't that 280, not 380?
Thank you, Lila. So that's the minimum. So in this problem with no context, we've no idea what's going on here, but the minimum value of C is this corner here, that corner in the vertex, in the feasible region, that vertex in the feasible region. This time all of our constraints were greater than, so that's why we were looking above, remembering that we shade outside the feasible region. The feasible region is the bit that's left unshaded. The question went on to say,
given that the objective changes, so it changes to 2x plus 3y.
Draw a suitable objective line and use it to identify the optimal point and the optimal value. Right.
So this is the alternative way of finding our solution. If we used it with this and the old objective, we would have got the same answer. It doesn't give you a different answer, but they've changed our objective. Okay. So none of our constraints have changed, so our feasible region isn't going to change. And we could still use the vertex method. This is why I'm always a bit, I'm not sure this is necessary, because I think what we've just done is by far the easiest way. But anyway, we'll do what we're told. So what we do is this. We pretend that we know what the profit's going to be. Now, we already know it's going to be, in the high 200s, low 300s. But I'm going to pretend that C is 120. I chose 120 because it's divisible by 2 and it's divisible by 3. So I'm going to draw that line, okay? I invite you to do the same. Draw that line on your graph, add it to the graph. That line there.
So, and I could have used any value. I could have used any value. X is nothing, and Y is nothing. On my graph, that's that black line.
Now, I've got the skills to work out the gradient of that line. I can rearrange it so I've got just the y on its own, and then I can divide by 3. So I know that line's got a gradient of minus 2/3 and crosses the y-axis at 40. What if instead
The profit was
240, not 120? What if I said draw me that objective line? What would change about that line and what would not change about that line? Jack. So if I changed 120 to 240 and went through this process again, what would change about the black line and what wouldn't change? So
I've just rearranged the original line for 120. I've shifted the minus 2x, shifted the 2x over. If I change that to 240, what is going to change about that and what won't change about it?
It would move like sort of upwards, wouldn't it?
So, okay. So are we happy that 2x plus 3y equals anything will have the same gradient as that line?
So all we need to do in order to find our optimum point is change that value. Okay. Now remember, we've changed our this. This has changed from before. And if this was a maximised problem, we would slide it up until we found the last point in our feasible region, because that would be the biggest value that was in the feasible region. In this case, because this is a minimised problem, we want to slide it up until we reach the first corner. So that's going to be there.
Now, up at Desmos, what you are expected to do is take your ruler, put it along the line that you've just drawn,
And just slide it up parallel.
and use that to identify which of the points, in this case, what's the first point that you cross?
And
In this case, it's that point there, which I've rubbed off with it. It was 90/30. And so that's, using the objective line method, we can identify which of our corners gives us the optimum solution without having to work out all of them. So I picked any number to go there and drew the line, and I knew that if I varied that number, it wasn't going to change the gradient, it was just going to change the y-intercept.
And so I could use my ruler just to slide up through the feasible region. And in this case, it's a minimised problem, so I'm looking for the smallest corner. So the smallest corner is there.
Using this, it gives me 270. 2 lots of x plus 3 lots of y. C is 270. Right, one more. 166, question 4. Now, again, it just so happens that every corner of the feasible region was an integer there. So let's just look very quickly at the question where that is not the case.
166. 166 question 4. Here we are. So can I get you to try and formulate this. So write me some constraints. Shall we agree that x is the number of type A's? X is the number of type A's. And y is the number of type B's. Okay, so see if we can formulate this problem. Is that a bit bigger? No, it's not bigger. Now, there's some really quite fiddly wording. I always think when it says things like at least, I always have to think really hard about which way my signs are going to go. Has anyone managed to come up with a constraint relating to the length? What have you got, Ben?
I know I've got that there.
Right, yeah, so it's 1x plus 1.5y. I've done it, what you said is exactly the same. Yeah, yeah. It's got to be at least 30 metres long. Now that's interesting, I don't know whether that means it could be infinitely long, but it's got to be at least 30 metres long. We're then, we're told that he wants at least 6 of type B, so at least 6 means that. But has anyone got a...
For that one, go for it. What, did you get it the right way around?
Is it x is greater than or equal to 2y?
It is indeed, yeah, it is indeed. Now, and of course, they've both got to be greater than 0, and actually, that's a bit of a nonsense thing anyway, because x has got to be greater than 6, and y has got to be greater than 6, so actually x has got to be greater than 12, but I'll put that one in there. And it's got to be a whole number. It's got to be an integer. Where does it say that? It's really good. Well, I suppose, yeah, you can only buy. So we've got to have an integer solution. So we've got 3 lines to draw. This one is but the y equals 6 line is quite nice and easy to draw. And this one, well, the line we need to draw is that, which I'm going to rewrite as y equals a half x, because I know that's a line with a gradient of a half that goes through 0, 0, goes through the origin. So just very quickly, see if you can
draw me that graph. I reckon your axes need to go as far as
30 on the x-axis and 20 on the y-axis. Now, I'm only doing this because we're running short of time, but there are my lines. So we need to be above the y equals 6 line. So we're above that green line. And we need to be above the red line, so above the green line and above the red line. Now, you've got to be careful here. If I plot the y equals a half x, it's actually where y is less than or equal to a half x, isn't it? Flipping that around. So I need to be underneath the blue line. So my feasible region is above the green line, above the red line, underneath the blue line. So it's this region here.
But this presents me with a problem. And what I think I might do is I might share this with you in Desmos. I'll send you an email and you can click and open this graph. But Desmos, you don't need to open an account, you'll open in the browser. Because we can't just look at the corners. We've definitely got a whole number corner here. That looks to me like 21, 6.
But this corner here isn't a whole number. This corner here isn't a whole number. So what I've got to do is move in to find whole numbers near it. And actually there's a couple. There's one there and there's one there.
This one is 18.
Is that 18.8 and that's 18.9. So that's 18.8 and that's 18.9.
So those aren't corners, but they are the nearest
integer values to the corner. You've got to be clear when you're solving these problems, is it a problem where x and y have to be whole numbers, or is it not a problem? So that was our objective, to minimise that. So I invite you to have a go at seeing if you can work out which of those, I mean, I'm hoping it's fairly obvious which of those two are going to be the minimum. But, you know, a toss-up between which of those and that, which of them gives you your optimum solution. So that was page 166, question 4, and 5 and 6 are similar practice. I wouldn't worry about all the guff in between the first problem we did, the Mrs. Cook problem, and these ones. They sort of build up. But I think because of your particular set of skills, as Lee Leeson would say, you'll have no trouble. You'll have no trouble. Good stuff. There we go.